In this lecture, we are going to introduce one more type of compactness, which is called local compactness. Let's begin with the definition of locally compact topological space. Let's say X is a topological space. X is a uh, topological space, and here is the definition of locally compact space. X is a topological space. then the space the space X is said to be locally compact it an element X of the space X if there is some compact subspace C of X that contains a neighborhood of X. So this is the definition of locally compact space at a point in it. Let's describe this definition using a picture. Let's say I have a topological space X. And let's say X is a point. This lowercase x is an element in a topological space X. Then we call that X is locally compact at X if there is a compact subspace C of the topological space X such that this C contains a neighborhood of X. If this topological space X satisfies this condition, then X is called X is said to be locally compact at X. X is a topological space, and this X, lowercase x, is an element of this topological space X. Then this topological space X is said to be locally compact at this point C if there is a compact set C or the compact subspace C of X such that this compact subspace C contains a neighborhood of this point. And if X is this topological space is locally compact at each point of X, then the space itself is called locally compact. And if X is the topological space X is locally compact at each point of if X is locally compact at each of its points, then X is said to be locally compact. That means if the topological space X is locally compact at each point of the space, then X itself is called locally compact. That means no matter which point you pick in X, there should be a compact subspace C of X such that C contains a neighborhood of that point. Now let me give you a couple of examples of locally compact space. Example number 1, a compact space is locally compact. This is quite obvious result. If you have a compact space, then that space is locally compact. You can see here, let's say I have this topological space X, which is compact, and we are saying that this space is locally compact. If it is locally compact, then by definition it has to be locally compact at each point of this topological space. Let's say this X, this is an element in X, or this is a point in X. Then we can say this X is locally compact at this point. This is an arbitrary point in X. Then we can say that space X is locally compact at this point X if there is a compact subspace of X containing or there is a compact subspace of X that contains a neighborhood of this point X. Since X is compact, so X will serve as a compact subspace of X that will contain a neighborhood of X. Since in order to be this space locally compact at X, we need a compact subspace of X that contains the neighborhood of this point. But X itself a compact space, so X will serve as that compact subspace which will contains a neighborhood of this point, so that X is locally compact. Here is another example. Let's consider the real line R with standard topology, which is also the order topology, because the standard topology and the order topology, they are same on R. Consider R with the standard topology, then R is locally compact. Then R is locally compact. You can see here why it is locally compact. Let me use this picture here to describe this result. Let's say we have a real line. This is positive infinity and that side is negative infinity. We are saying R with the standard topology is locally compact, and we know that is in the standard topology the order the basis element or the open set in R, they are open interval of this form A to B. Okay, so if R is locally compact, then it has to be locally compact at each point in R. Let's say X is an arbitrary point in R. So now we need to show that R is locally compact at this point X. If it is locally compact at this point X, since X is an arbitrary point, then we can say that R is locally compact at each point. Now why R is locally compact at X? So if it is locally compact, then there should be a compact subspace of R containing a neighborhood of X. And we know that each closed interval in R is compact. So let's consider this closed interval X minus 1 with the left endpoint and X plus 1 with the right endpoint. Then obviously this closed interval will contain X. Okay, so this is this interval from X minus 1 to x plus 1 that will contain x, and since it is a closed interval, so it's compact. So we found a compact subspace of R, and then this compact subspace should contain a neighborhood of this point X. And we know that in R, the open set are simply the open interval. Now, let's take this open interval, x minus 1 with left endpoint and right endpoint is x plus 1. So this is open, and also it contains this point X. So this interval is a open neighborhood of X, and obviously this open interval is a subset of this closed interval. So this closed interval will serve as a compact subspace of R which contains this neighborhood of X. That's why R is locally compact at X. Since X is arbitrary point, so that R is locally compact at each point of R, thus R is locally compact. Just let me write down the thing that I just described here. Then R is locally compact since X, which is an arbitrary element in R, lies in the neighborhood NBD, that means neighborhood x minus 1, x plus 1. This is a neighborhood because it's open in standard topology and also contains x. Is a neighborhood of x which contains in the compact space x plus 1, x minus 1 to x plus 1. So this is another popular example of locally compact space. So R with the standard topology is locally compact. And we have seen in the order topology lecture, R is a simply ordered set, and that has a least upper bound property. So here R is a simply ordered set, which we have seen in the order topology lecture. R is a simply ordered set because the strictly less than strictly less than is a simple order relation. So R is a simply ordered set that has a least upper bound property. So here what I'm trying to say is, since R is a simply ordered set with least upper bound property, so that R is locally compact. Not just the R. In fact, if you have any simple ordered set with least upper bound property, then that set or that space is going to be locally compact. So that's our next example. Okay, example number 3 is also a very popular example of locally compact space. Every simple ordered set X having the least upper bound property, is locally compact. Now you can see here why this is true. Okay, let's say we have X, which is a simple order set, and that has a least upper bound property. If X is a simple order set having a least upper bound property, then if we consider order topology, on X, then the a basis element for the order topology on X, they are going to be one of those set, like this open interval. If there is no least element, or if there is no greatest element, and if there is a least element, then the basis element is gonna be this half open interval, and if there is a greatest element, then the basis element is gonna be this half open interval. So the basis element for the order topology on the simple order set X is going to be one of these interval. Okay, now here we are saying that this X, which is the simple order set that has least upper bound property, is locally compact. It is locally compact, then it has to be locally compact at each point of this set. Let's say X is a point on X. Since those interval, they will form a basis for a topology on X, so this X is going to be in one of those interval. That's the definition of basis. So then X is this element X of the set X is going to be in one of those interval. All right, so those interval will serve as a neighborhood of this point X. Now what we need in order to be this X locally compact at X, we found the open neighborhood, we found not open, because all the neighborhoods are open. So we found a neighborhood of X. Now we need the compact subspace of X that contains that neighborhood. Now we know that if we take the closure of those basis element, then the closure is going to be a closed set. And and if you have a closed set in a simply ordered set that has least upper bound property, then that closed set is going to be a compact set. So the closure of each of those open interval or each of those basis element, that's gonna be a compact subspace of X is being a closed set in the simply ordered set. So the closure of those basis element that will serve as a compact subspace of X that contains the neighborhood of X. That's why X is locally compact at X. And since X is an arbitrary point, so we can say that X is locally compact at each point of X, thus X is locally compact. Okay, now just let me write down the thing that I just described here. Having the least upper bound property is locally compact since a basis element for the order topology, since the basis element for the order topology in X is of the form this open interval if there is no least or greatest element, and this half open interval or this half open interval, this one if there is a least element and that one if there is a greatest element. Since the basis element for the order topology in X is of this form, and closure of any basis element is a compact subspace of X. Its least upper bound property is locally compact since a basis element for the order topology in X is of this form, and closure of any basis element is a compact subspace of X. It's being a closed subset of simply ordered set X that has least upper bound property. Now here, So we found the neighborhood of any point in X, which is going to be one of those interval. Then the closure of those interval is compact. So the closure of this interval will serve as a compact subspace of X that contains those neighborhood of the arbitrary point. That's why X is locally compact at each point. Then we can say that X is locally compact at each point of X. Okay, and hence X is locally compact. All right, now let me give you one more example, but this time I'm gonna give you an example of a space which is not locally compact. The set of rational numbers, which we denoted by Q, is not locally compact. All right, so far in this lecture, what we did is we defined locally compact space, and I gave you few example of topological spaces which are locally compact, and one example of a topological space which is not locally compact. Now I'm going to give you a theorem. That theorem will describe the a relation between compact Hausdorff space and a locally compact Hausdorff subspace of the given compact Hausdorff space. And we are not going to prove this theorem, but if you are interested in proof, you can take a look in Munker's book. So here is a theorem. As I said before, this theorem will give us the relation between a compact Hausdorff space and its locally compact Hausdorff subspace. So here is the statement. Let's say let X be a topological space, then X is locally compact Hausdorff space, if and only if there exists a space Y, satisfying the following conditions. The first condition is X is a subspace of Y. The second condition is if we remove X from Y, the result has to be Y minus X. If we remove X from Y, the result has to be a singleton set, consists of a single point. And the third condition is Y has to be a compact Hausdorff space. So compact Hausdorff space. So this theorem it gives us a relation between compact Hausdorff space and its locally compact Hausdorff subspace. We are not going to prove this theorem, but if you are interested in proof, you can take a look in Munker's book.